Okay, as I said, it will be a short introduction into confocal microscopy. And I'm sure many of you are already using confocal microscopes. So this will be a small refresher of the theory of confocal microscopy. And for those of you who are using more wide field microscopes, this will be a good opportunity to learn something more about confocal microscopes, to learn about the benefits that these microscopes might give you in your day-to-day work. So in this first slide, I'm just giving you an overview of different things that you can do with a confocal microscope, and I will go through many of these things and say a few words. So confocal microscope is not only an imaging system; it can do many more things. But the most important criterion how to choose which microscope you want to use is basically your sample. You need to know your sample in order to decide what microscope you want to use. So as a rule of thumb, if you have a thick sample that you cannot, let's say, cut into small thin slices, then you will probably want to use a confocal microscope, because this microscope will give you the opportunity of doing optical sectioning. So as a first introduction, what is the basically difference between let's say a normal wide field microscope, which is using the camera to see your sample, and a confocal microscope? Basically, in the a typical wide field microscope, where you use a camera to detect your sample, you can basically get your image at one snap. So you take an image, and the image is immediately there on your screen. This is nice, but as you can see from this example, you don't only see your sample. You don't see only the things that are in the focus of your sample, but you see also something that is below and above the focus plane of your sample. So you see a lot of this off focus background in this image. On the other hand, using a confocal microscope, you need to invest a little bit more time in scanning your sample. So confocal microscopes are also called laser scanning microscopes. So basically, you're scanning over your sample. You need to invest a little bit more time, because you're scanning point by point. But if you compare these two images, these two examples, then you can see a clear difference, that now with the confocal microscope, you only see those things that you want to see, that are in the focus plane. A little bit of history. So the principle of confocal imaging was patented by Marvin Minsky in the 50s, and basically what he wanted to, or what his proposal was, is to use a light source, and then to put a sort of a pinhole in front of the light source, and then to put also the pinhole in front of the detector. So if you kind of look closer, if I just turn this image a little bit upside down, you will see that the basic concept of the confocal microscope didn't really change from the 50s until now. The only difference is that we nowadays use laser light as a light source, so we don't need a pinhole. The light is small enough, but basically the rest is kind of stayed the same. So how this optical sectioning is working at all? If you have a light source, in our case, you have a laser, and you want to image your sample, the light from the laser will get through several optical setting or optical hardware in your system, will be led to your sample, and then the light from your sample, independent on where the light comes from, will go back to your microscope and to some sort of detector. Now, in a normal wide field microscope, you will collect the signal coming from your focus of the sample, but you will also collect signal coming from up or down, or below or above your focal plane. In the confocal microscope, what we do is basically we utilize a piece of hardware which is called a pinhole, and this pinhole it's a mechanical hardware part of your microscope, and this pinhole is actually rejecting everything that is coming below or above your focal plane. So it's letting the light only coming from your focal plane go to the detector. So in this way, the pinhole diameter is determining how thick or how thin your optical sections will be, but it also determines how much signal is reaching your detector, because you're basically rejecting the light coming from your sample. And as a rule of thumb, and in imaging everything is sort of a compromise. As a rule of thumb, 1 Airy unit is a good compromise between getting enough signal on your detector and getting thin enough slices. I will come to the Airy unit in a second. I just wanted to mention this. So why are confocal microscopes actually called confocal microscopes? Well, it's a very simple explanation. So the pinhole is sitting at exactly the conjugated focal plane of the microscope. So from the combination of these two words, the confocals got their name. So pinhole is basically the heart of the microscope. This is what makes one microscope a confocal microscope. So it does the optical sectioning, but it's also rejecting some amount of light. When we are talking about Airy units and Airy disks, I just wanted to quickly show what I mean by Airy unit. So if you have a point emitter, if you have a single fluorophore or a single fluorescent protein, this object, which is a point, will never be seen in the microscope as a point, but it will be seen as a point spread function because of the limit of the diffraction. So after going through all the optics in the microscope, your point will be seen as a diffraction limited object, and this point spread function is also called Airy pattern, named after the scientist George Airy, who actually first explained theoretically this phenomenon. The bright central region of this Airy pattern is called Airy disk, and the size or the diameter of this Airy disk is referred to as 1 Airy unit. So it's this bright region in the middle of the Airy pattern, or if you look at the cross section of the point spread function, this is the this middle peak of the cross section. So this would be 1 Airy unit, and this is a good enough compromise. The other word in the laser scanning microscope is actually scanning. And what does it mean? It means that every laser scanning microscope has mostly mirrors that are galvo mirrors or galvo scanners. And what they do is they lead the laser light over your sample point by point. They can move the laser beam very fast and very extremely precise, and scan the laser light over your sample point by point. So now we have the laser. We are scanning the laser over the sample. The signal is coming back only from the focal plane of your sample, going to the pinhole, but we need to somehow see. We need to detect the signal coming from your sample. So how do we do this? How do we detect the signal in the confocal microscope? We do that using different types of detectors, but all of them are in essence photomultiplier tubes. And what they do is what their name says, is they are multiplying photons. So when your sample is emitting light, this light is actually in form of photons. And when the photons hit the entrance of the detector, the entrance of the photomultiplier tube, at the entrance of this PMT is a photocathode, where a so-called photoelectric effect happens. So in this photoelectric effect, the photons are being basically transcribed into the electrons. Now these electrons are being led inside the PMT. They are reaching the insides of the PMT, where you have dinodes. And these dinodes, this is a cascade of dinodes, which are, each of these dinodes is more positive than the previous one. So the electrons are being led through this cascade. They're being multiplied and at the end, the signal that we can measure with our computers is in sort of electricity, and we get a certain pixel, which will be more or less bright depending on your sample. So if you have a very bright sample, you will have not only one photon, but you will have many photons coming from your sample. These many photons will be translated into many electrons, and at the end of the PMT, or at the end, you will get a bright pixel without applying too much power into the detector. Now, if I apply the same gain to my detector, but I have a dimmer sample, so I have less photons, then the pixel that I get at the end will be a little bit darker, because I didn't amplify these electrons too much. What I can do, if I don't want to increase the laser power, if my sample is sensitive, I can actually increase the gain of my detector. So I'm increasing this multiplication of the electrons inside the PMT, inside this photomultiplier tube, to increase the signal from my dim sample. So with the increased gain, I will get a brighter pixel. However, you should always be careful with putting too much gain into the detector, because if you have a very, very dim sample and you try to just put more gain into the detector to see a bright pixel, you might see the bright pixel, but the signal coming to this bright pixel might not be coming from the sample itself, but they are actually so these electrons that make the pixel at the end, they are being generated inside the PMT. So you should always be careful not to go to, let's say, 100% master gain. So I mentioned in the beginning, there are different types of detectors, and they all depend, it all depends basically on this first step of translation of photons into electrons. This translation is never 100%. It's actually never 100%, but you can have different detectors that are able to translate, let's say, photons into electrons with a different efficiency. So one of them is the classical multi-alkali PMT. It's a standard PMT which has a very wide spectral response. So it can translate, let's say, UV to near infrared photons into electrons. And it's called multi-alkali because basically this photocathode has these four alkali elements. Now, this is a classical standard detector. Of course, there is something that is called a gas detector. So there is it's a different different material of the photocathode, And this gas detector has a 2 times better quantum efficiency compared to the multi-alkali PMT. You can see it here in this middle range of the spectrum. It's a double the quantum efficiency. What does it mean in real life? Well, if I now take an image with my multi-alkali PMT and compare it with my gas detector, you can see clearly from these two examples that the image on the left has much more background. And even if I draw a line, if I draw like a profile line over the same piece of the sample, you can see very clearly that the signal to noise ratio using the gas detector is much higher compared to the multi-alkali PMT. Now, this doesn't only mean that I have a nicer image, because nice images are one thing, but this also means that since I'm having higher signal to noise ratio, I'm able to scan faster because I don't need to spend too much time on one pixel because I'm getting enough signal with the gas detectors. That means I'm getting my images faster. I don't need to, let's say, average. I don't need to expose my sample too long to the laser light. At the end of the day, I will get my data faster, and I know that time, especially in imaging facilities, is a limiting factor. So all these things need to be taken into account when you think about gas detectors. But it's also that since I'm having a bit better signal to noise ratio, I can maybe reduce the laser power, so I can image longer my sample because I'm reducing the bleaching or some phototoxic effects. So I can observe, let's say, live cells for a longer time. So the confocal microscopes are, as we already heard so far, not only limited to thin cells or layers of cells. This is the example of central nervous system of a cockroach, and it's been optically sectioned with a confocal microscope, and then 3D rendered using the Airyscan software. And then you can really see the nice details of your sample. I mean, this is also a very big field of view, so you can take also several tiles of the sample and stitch them together. So all these nice images, when we talk about nice images, most of the time people mean, oh, they're nice and colorful. So the confocal microscopes are probably the most dominant systems used in the labs today. And one of the ways how you can, let's say, produce these nice images, if we call it nice images, is fluorescent labeling. So what is a fluorescence? There are a few ways how you can explain fluorescence to somebody, but at the bottom line, it does look pretty. Anything that you do with fluorescence looks pretty. And fluorescence is not actually something that we know since a few years. The first time fluorescence was described was actually in the 16th century. So even back then, people knew about fluorescence. And the cool thing about fluorescence is the existence of Stokes shift. So if you have a fluorophore or a fluorescent protein and you shine a light with a certain wavelength, this fluorophore will go into the excited state, and on the way back to the ground state, this fluorophore will emit light which is now different wavelength from the light that we use to excite the fluorophore. So this shift, this distance between the excitation and the emission light is called Stokes shift, this phenomenon. And this is actually something that we use in the fluorescence microscopy because now we are able to physically separate the incoming light from the light coming from your sample using certain optical elements, for example, beam splitters. What is also very important to mention, and I like to mention it every time I give these kind of talks, is how to read the fluorescence spectra. So you got your fluorophore, you got your fluorescent protein, and then you go to some spectra viewer, and you look at the excitation and emission spectra of your label. But what does it actually mean for your daily life? So in this example, I have a GFP fluorescent protein, and if I look at the excitation spectrum of the GFP, it has the maximum at about 488 nanometers. Now, if I use my 488 nanometer laser, I will get a nice emission of my GFP, which is shifted towards the longer wavelength. But what if I don't have the 488 laser, but I only have 405 nanometer laser? Well, I can still excite the GFP. I will get some kind of excitation at this range of the excitation spectrum. Of course, the emission spectrum of my GFP will be much lower in intensity, but I will still get my signal. So this can have positive and negative effects. Basically, you don't always need the exact same laser line to excite your fluorophores. So you don't have to be exactly precise with the laser line. You can still get the signal from your sample. But on the other hand, if you have the two different fluorophores in the sample, and you need to use both lasers for your sample, then you need to be careful with avoiding the crosstalk, because assuming that you have a DAPI fluorophore here or Alexa 405, you will need to turn on the 405 laser, and by doing that, you will also get some signal from the GFP. In more cases than not, you will have actually more than one fluorophore in your solution. So you will have to use several lasers. And in extreme cases, I think people were able to image actually 10 or more fluorophores at the same time. The challenge of this multi-fluorescence imaging is, as we saw previously, the crosstalk that you get. Of course, this is a very extreme case, but the amount of labels present nowadays is extreme, and you can really go wild with labeling different pieces of your sample. Even here, confocal microscope can help you by doing something that we call unmixing, linear unmixing, or spectral unmixing. By using, for example, spectral detectors, you are able to separate these colors where you get the crosstalk. And in just give you one example, this was a plant cell. So plant cells, for those of you who are doing plant cell research, you know that imaging plant cells is might be very difficult, because plant cells have autofluorescence in chlorophyll. But actually, this plant cell was labeled with four fluorophores, or 4 labels. You can see it here. And using the linear unmixing, so just doing, let's say, a typical confocal imaging, but then doing some extra analysis on your images, they were actually able to separate all those 4 labels plus the autofluorescence chlorophyll. So it's not only getting a nice simple images of your sample, but it can also, the confocal microscope can also help you image a very challenging samples. Now, there are many processes in biology which we can observe or analyze with different techniques. And one of these techniques is definitely microscopy. But in microscopy, we don't always just do nice images. We can also get some numbers from the microscopy. And if you start asking yourself, how many proteins do I have in the membrane or in the cytoplasm? How fast do they move? What is the mechanism of the movement? What is the interaction between different proteins? All these questions can be answered using a confocal microscope without changing, basically, without changing your sample. One of the more used techniques in many labs is FRAP, so fluorescence recovery after photobleaching. And in FRAP, you basically park, because you have the scanners that are scanning your laser. You can park your laser in a certain position of the cell. You can apply the high laser power to bleach it, and then you will observe this point of your sample and observe how fast the fluorescence is recovering in this sample. So in this example here on the right, they were actually bleaching this spindle and then looking at the fluorescence recovery. So you can have different information after that. So you can get the information: what is the immobile fraction of my protein of interest? What is the mobile fraction? How fast this is happening, and so on. There are many different photo manipulation techniques, all based basically on the same idea as FRAP. There is, for example, photo activation, where you park your laser beam to a certain position of your cell. You apply a certain laser line, and this is activating proteins in this region that can be then that become fluorescent. Or, for example, the photoconversion, where you apply the laser light, and there is a conversion of the color of your sample. So all of these are basically based on FRAP experiments. The other technique that will also give you some kind of numbers, it won't necessarily give you nice and colorful images, but it will give you a very nice data from your sample, is FCS, fluorescence correlation spectroscopy. In FCS, you basically, it's a spot scanning, or it's a spot technique where you park your laser at one spot in your cell or in your solution, and then if big molecules or some oligomers are passing through through this observation volume, they will create a sort of a time trace. If you now have a very small molecule, it will also create a time trace that is different compared to the big molecules. And by doing some correlation of these time traces, you will get a typical FCS curves. And what you can read from these FCS curves is really nice. You can read the concentration of your protein of interest. You can read how fast it's moving through your sample, but you can also read what is the type of the movement. Is it a protein in a membrane? Is it active transport? Is it some kind of anomalous diffusion? So all these things can be done using a confocal microscope, parking your laser beam at one point and doing the time trace. So you will not necessarily get colorful images, but you will get lots of information about your sample. If you, so as I said, FCS is a spot technique. If you are more interested in the whole context of the whole cell, let's say, there is another technique that is very similar to FCS. It's called RIX, raster image correlation spectroscopy. And in this technique, what you actually do is you don't correlate the time traces, you correlate pixels. So you make a you scan your image multiple times, so that you can have let's say time information, and then you correlate not the time trace, but you correlate pixel to pixel, and what you get at the end is a kind of a heat map of your sample with in this example different diffusion coefficients in different pieces in different parts of your image. So we can do a nice optical sectioning. We can do 3D imaging of very thick samples. We can separate many colors. We can get some nice numbers, so not only nice images, but you can also get the very nice numbers. It's a very analytical tool. So you might think that we are kind of at the end of the improvement of the confocal microscope. This is of course not true. So we still didn't reach the limit of confocal systems, and we are trying to kind of approach this by using a new type of detector, which is called Airyscan detector. So a few years back, we actually did a little survey, and we asked more than 200 researchers who are using confocal microscope what they need in their everyday imaging life. What is the limiting factor? What would they need? What would they like to improve in their confocal microscope? And you can actually see that all of these things are basically very important. You want to have a sensitive system. You want to improve the signal-to-noise ratio. Of course, you want to improve the resolution, and of course, you want to improve the speed with which you're taking the images. So it's kind of difficult to improve all of these things at the same time, because if you let's say want to improve sensitivity, you might go down with the scanning speed, so you can collect more light. So is there a way how to improve all these things at the same time? So this was the example from one of the customers who are studying the telomere replication. And if we zoom into these telomere regions, you don't really, with a typical confocal microscope, you don't really see what's going on in this region. Using the Airyscan detection, they were actually able to see the details of the tips of these telomeres, so as seen as 2 points actually, compared to the previous image. You want to have a gentle imaging, of course. Every time you do imaging, you want to be gentle to your sample. So you don't want to shine too much light into your sample, because you might photo bleach your sample. You might increase the temperature, which could be toxic to your sample. So all these things are very important, in addition to having a high resolution, having good signal-to-noise ratio. But what came up, especially in the last few years, is that you want to see the context. You want to maintain you don't want to look at only one cell and then draw conclusions. You want to look at the whole brain. In this example, the researchers were studying the fluid flow in the brain of the mouse. And what they were able to do in 2016 is to image this part of the brain. In 2019, they were able to image much bigger part of the mouse brain. And what they were actually looking at, they were looking at the movement of these little cilia in the chambers, and they could actually at the end create a sort of a map, a network of the speed and direction of the movement of these cilia. They could also see the asynchronicity of the movements of these cilia. So having this one image is, let's say, easy, but what you want to have is a big picture. You want to have the whole brain, and you want to have the context. We go from culturing the cells to culturing several layers of the cells towards, of course, model organisms. And all of these things can actually be done using the Airyscan detector. So it will give you the opportunity to increase signal-to-noise ratio, to increase the resolution of your image, and to also scan very fast over your sample so that you are able to scan bigger areas of your sample. The addition of the Airyscan detector to a confocal microscope is not it's basically not a rocket science. Basically, you just add another detector to your confocal microscope. Nothing changes. You still have your traditional confocal microscope, and now you have, in addition, an Airyscan detector. And how does this detector work? Basically, when using Airyscan, we are saying goodbye to the pinhole. So normally you would have a compromise of opening the pinhole to one Airy unit and imaging a sample. Now with the Airyscan detector, you have actually 32 small detectors. They are all 32 gas detectors, so they are sensitive detectors. And each of these detectors have approximately the size of 0.2 Airy units. So each of these detectors is making very thin optical slices. So each of these detectors is increasing the resolution. But all together, these 32 detectors that are kind of arranged in a surface, they collect the light of more than one Airy unit. So there is no need to compromise at this point, because you can simultaneously improve the resolution and the signal that is reaching the detector. And how the detector works is basically each of these detectors is taking the image of your sample from different point in space, and all those 32 images are then put together back into the center, and with a little push of the Airyscan processing, we get a high resolution. So as an example, I put here only, I mean, not realistic examples, but let's say we take these 6 detectors, the 6 small detectors in the Airyscan when we make an image of your sample. So these 6 images are just overlapped, and they are playing one after the other in this first movie on the left. You see that they are shifted because, of course, you're looking at your sample from a different angle. This shift becomes even more obvious the more you go towards the outer rings of the Airyscan detector. So what you basically do, you take an image of your sample from a different angles. In this case, the signal that you get from very outer ring of the Airyscan detector is, of course, a little bit lower because you're looking at your sample from further away, but it still contributes at the end to the big picture. And we are still not, or you could maybe assume that these are some kind of beads. But if I now take a real Airyscan image with each of these 32 detectors and do the processing, you can actually see what the image looks like, and you can see these fluorescent beads. So these are 170 nanometer fluorescent beads. If I now compare this to typical confocal image, so in a confocal microscope, if you have 170 nanometer beads, you won't be able to reach this resolution, because using confocal microscope, you will have this kind of a resolution. Now, if I just do Airyscan image and I take these 32 images and put them back into the center, so to say. So this is the first step of Airyscan processing, so-called pixel reassignment. I already get improved resolution. And now if I take, if I do the last step of Airyscan processing, so I take, I process each of these images, I get, compared to the confocal microscope, I get 2 times a higher resolution with the Airyscan detector. Now, this is of course not everything that you can do with the Airyscan detector. There are several ways you can image your sample using the Airyscan detector in the multiplex mode. Multiplex mode means that you are you're basically taking more than 1 pixel at a time. And as you can see in this little movie, in the mode which we call 8Y, what you do is you use a slightly elongated laser beam in a way that you can actually, in one scanning point, receive 8 pixels and not only 1 pixel. So you are speeding up the acquisition of your sample by 8 times. And of course, you are using the Airyscan detector, so the resolution and the signal to noise is also higher. So you are able to image your sample much faster. And this is the example of cardiomyocyte cells, and they were actually interested in buckling of microtubules. And the image on the left was done some years back when the Airyscan was not working in the 8Y mode. The image on the right was taken with the 8Y mode. It doesn't, it's not only that we say, okay, we can image faster because we can. This also means that you can image larger field of views because you are fast, because you can capture these this information from your living sample. And not only that, we can do the bigger field of views, but we can also do it with different colors because we are fast enough to image simultaneously different colors. With this, I would like to finish my talk. As the reminder, I put the slide that I showed you at the beginning. So all of these things that I talked about today were done just using a simple confocal microscope. There was no changing of the sample preparation. There was no changing of, let's say, embedding your sample. There is no changing of your well plates or your slides. So all of these things that I talked about today are just clicks in the software. So, and I didn't even talk about everything that you can do with the confocal microscope. Of course, you can also use multiphoton lasers, so you can image even deeper into your sample. You can couple pulse lasers to the confocal microscope, and you can do film imaging, so time-resolved imaging. You can combine the images taken on the confocal microscope with the wide field microscope, with the electron microscope, microscope. As you can see, the confocal microscope is a very versatile, and there is a reason why the confocal microscopes are working horses in many labs nowadays, because you can do so many things without changing basically anything. With that, I thank you for your attention, and I'm open for questions.